right? We got to have some sort of an experiment. An experiment has to have some sort of element of chance. You're going to do something. Classic things are like rolling a pair of dice, or you have a deck of cards. You're going to mix them all up, and you're going to randomly pick one card, right? Those are the classic kinds of things that we study when we're looking at examples of experiments. Experiment could also be something like you randomly call a person and you ask them something, like a survey. All kinds of experiments that we can use, but in particular we often use dice and cards and things like that. Okay, so we establish what the experiment is. We establish that it's got some sort of element of randomness associated with it, right? So we examine the situation and identify all the possible outcomes. And then if we write down all the possible outcomes, we get the sample space, right? So the sample space is made up of all possible outcomes. Okay, so sample space, we get all possible outcomes from our sample space. That in some cases is a lot of work trying to figure out all those things, right? As far as notation goes, we often refer to these little things as little e's. E sub 1, E sub 2, E sub 3, dot, 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 dot. So our sample space often is referred to have n number of things in it. So maybe out to E sub n. Okay. So those are our possible outcomes, and from those we think about subcollections of those, which are events. So from there, we're looking at events. Events. And events come in two shapes. One of them is simple events. Simple events. And compound events. The difference is that with a simple event, it's an event that is described by a unique outcome, by a single outcome, which is why it's called a simple event. So only one outcome happens to describe it. If I'm rolling a single die, six-sided die, the simple events are that it's a 1, or it's a 2, it's a 3, it's a 4, it's a 5, or it's a 6. If I'm drawing a deck, one card from a standard deck of cards, then any one of those cards could be a simple event. And now compound events are made up of a combination of those outcomes, right? Combination of several outcomes. Any questions about these? No? No? Usually we then denote these as little e sub 1, e sub 2, dot, dot, dot. And then usually we reserve this for capital letters. Compound events are used with usually capital letters. Okay, once we identify our experiment, our sample space, identify events, then we want to try and find probabilities. So the first rule we found was the addition rule for probabilities. So, given event A and event B, then the addition rule involves the OR statement, so the probability that A or B happens. Well, that comes in two statements. In order to find that, we can use the general one. The general one is equal to the probability of A plus the probability of B minus the probability of A and B, right? We have to look at that overlap, right? This one is valid no matter what A and B, what sets they are. This is always valid. However, there's a little subcondition that if in addition it turns out that A and B happen to be disjoint, then this rule becomes a little simpler, right? So if we know event A and event B are disjoint, / mutually exclusive. In those cases, well then this formula simplifies just a little bit. Probability of A or B is equal to the probability of A plus the probability of B, right? So this part goes away because if they're disjoint, that means that that guy is 0. Good. We described them with Venn diagrams. So over here, we learned that we can describe this sort of a situation with a Venn diagram that maybe looks like this, where this is A, this is B, this is our sample space, and so here is event B, and here is event A, and they're disjoint, they have nothing in common. So here is a Venn diagram description of two events that are disjoint. And if they're not disjoint, then they have something in the overlap, something in common. So maybe we can describe them this way. A, B, S, and then there is something there, and then there is something there. Right? So there's something definitely in the overlap. Good. Given event E, all outcomes not in E are in E complement. Right? So everything not in E is what we consider E complement. We can do a Venn diagram description of this. Again, so if we have something like this, and we have event E right in the center, this is event E, then everything outside, everything out here, is what we would consider E complement. So E complement is everything out here. Good? Questions? So then we can say that E complement and E are disjoint. So note that E, right, event E and event E complement are disjoint. Right? That's true. And also note that event E and event S together make up the entire sample space, always. So it's also true that the number of outcomes in E plus the number of outcomes in E complement is always equal to the number of outcomes in our sample space. Right? Because they make up the entire sample space. They partition the sample space into two groups where they have nothing in common, they're disjoint, and together they make up the entire sample space, which means that the probability of E plus the probability of E complement must be equal to 100%. If you're going to randomly pick one outcome from that sample space, it's always true that it's in E or in E complement. Right? It's either in it or not in it. Those are the two choices. Good? So by that reason, we can use this simple statement to solve for one or the other. So we can use some simple algebra here and say that this is the same thing as E complement equals to 1 minus the probability of E. Or the other way around, we can say that the probability of E is equal to 1 minus the probability of E complement. Depending on the word problem, one might be useful versus the other. Good? Good. Okay, last rule, the multiplication rule. Right? This is involving this. You know, we want to find, so given event A and event B, find the probability of A and B. That's what we're after. Given event A and event B, find the probability of A and B. Okay? This comes in two flavors here. We need to know whether event A and event B are dependent. If event A and event B are independent, let's start with that one. Independent, if event A and event B are independent, then the rule is really easy. Probability of A and B is equal to the probability of A times the probability of B. So if we know that they're independent, very easy rule, right? Just multiply them like that. On the other hand, if we know that they are dependent, if event A and event B are dependent, then the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. Now we got to deal with conditional probability. Probability of A and B is equal to the probability of A times the probability of B given that A has occurred. Well, there's another way we can write the same thing because I know that here these two things can be flipped around. So I know that this is the same as the probability of A and B, which is equal to the probability of B and A, flipping them around, B and A. So this is equal to the probability of B times the probability of A given that B has occurred. Okay. So this multiplication equals that, and this is the same as that, and this is the same as that. So you can go in this sort of direction here, but they don't make, well, I mean, as a product, this product equals this product. So we can say that. But you can't mix and match the individual pieces. You can't say this piece equals that piece. That's not true. Not always. Good? Good? Okay, so it's really important for you to be able to determine the probability of A and B. You need to know whether you're dealing with independent versus dependent. So how do you figure that out? Well, that's where that test for independence comes from. Well, actually, before we get to that, so this equals that, which equals this, which equals that. And so now if we just take this over here and we want to solve for this, another common formula for finding this is, well, if you're given that and that, you can just divide them. And that's the definition of what this is. Same thing over here. We have this equals this product. So if you're given that one and this one, to find this one, you just divide it over there. So from here, we can say that the probability of B given A is equal to this divided by this. So it's equal to the probability of A and B divided by the probability of A. Right? All I did is I divided both sides by this guy. That's how we get that. And from over here, this right here, if you're given this and this, you can find this by saying the probability of A given B is equal to the probability of A and B divided by the probability of B. Good? Questions? We're good now? Good. Okay, so it's really important to be able to determine if A and B are dependent or independent because there's two different formulas for them. Obviously, the independent, the much easier of the two, find them separately, multiply them, that's easy. So in some cases, the situation will just let you know they're independent. It's obvious that the two events are independent. Like, for example, we looked at or we talked about the probability of winning the lottery and the probability of dying on an airplane. Those two things have nothing to do with each other, right? It's just common sense that they have nothing to do with each other. So if I want to know what's the probability that one individual both dies on an airplane and wins the lottery, well, just find them separately and then multiply them together. That's the probability that you get both. Got it? Good. But if it's not super obvious, how do we know? If it's not really obvious whether they're independent or dependent, well, that's when that little test for independence comes in. So, test for independence. event A and event B. So if you have two events, A and B, you're like, is this independent, is this dependent? Then what you have to do is the following. You have to find the probability of A given B, and if it turns out that this is equal to that, if that's true, then that means that A and B are, is that independent or dependent? So this is the case where the new information that B occurred did not affect your probability. Independent. And then the other way around, same thing. Probability of B given A is equal to the probability of B. So this newfound information made no difference at all. If this is true, then event if true, then event A and B are independent. Good? If it's not true, they don't equal each other, this is different from that, or the other way around, then they're definitely dependent. Good? So, write that down. The other way around, if the probability of A given B does not equal to probability of A, so there was some sort of noted difference, these two things are not equal to each other, or the other way around, probability of B given A does not equal to B, somehow they're different, the fact that we have new information changed our probabilities, now we can conclude that, so then event A and B are dependent. Good? Good. One last thing. Dependent, independent, mutually exclusive, not mutually exclusive. People confuse those all the time. So let's take a look at that case one more time. So back to this thing over here. We established that this is a case where they are disjoint or not disjoint. Not disjoint is up here, disjoint is down here, right? So this is not disjoint versus this one, which is definitely disjoint. Okay, well, can we establish something about dependence or independence based on that? So let's look first of all at this one. If they are disjoint, can we say something about them? Are they dependent or are they independent? Independent, is that what you think? Okay, so for instance, let's throw a real example on here. Let's say it's that basic one when we roll a pair of dice, right? Pair of dice is rolled, six-sided die, there's only 6 options. Let's say I bet money on the number 4. It's going to be the number 4, people. I put $100 on it. My friend, now he thinks it's going to be the number 5. Okay? What are the other possible options? Well, if a 1 comes up, we both lose, or a 2, or a 3, or a 6. Right? Those are the ways we both lose. Good? Alright, so the probability that I win is going to be what? Probability that the die equals to 4, which is equal to 1 out of 6. Good? Now we're going to see what happens. So he rolls the dice, right? And I can't see what's happening. There's just so many people in the way, I can't see. But I hear my friend yell out, I won! So now that I have new information, what's the probability that the die equals to 4, given that B definitely happened? Oh, so what happened to my probability? It was affected, right? So the fact that they're disjoint makes them dependent, right? It automatically does happen. The newfound knowledge, so the fact that the probability of A given that B occurred does not equal to the probability of A. Right? That's not true. Before I knew some information, I had a 1 in 6 chance of winning. But now that I know he won, Well, that brings me down to 0. And 0 doesn't equal to 1 over 6. So this automatically guarantees that A and B are dependent. And so event A and B are dependent. A and event B are dependent. That's always true. If we have disjoint, then that guarantees dependent. Always true, right? Because you know that the other one happened, you know you definitely didn't happen. Yes? Okay. On the other hand, if we have something like this, not disjoint, some sort of an overlap, then there's no clear conclusion. It might be independent, it might be dependent, we got to use our test. Either are possible, use the test. For independence. Good? So disjoint automatically gives you dependent, but not disjoint, all bets are off. You're going to have to try it out, use your test to see what happens. It might be dependent, it might be independent. Good? Questions? Okay, so that's it in a nutshell. No other questions? All right.